Hello, everyone. My name is Shudha Javlani. I'm a graduate student at Purdue University in the Electrical and Computer Engineering Department. I'm working at Spark Lab under Professor Shreyas Sen. I'll be presenting the paper 100 kHz to 1 GHz termination dependent human body communication channel measurements using miniaturized wearable devices. Exponential scaling of transistors has led to the proliferation of wearable devices. All of us use some form of wearable device like smartwatches, smartphones, Fitbits, and earphones. And some of us who have diagnosed medical conditions might use some wearable or implantable medical device like a pacemaker. All of these devices need to communicate in order to either be programmed, transfer data, or simply perform their task. The network created to enable this data transfer is called a body area network. Since the devices on body area networks have to be portable, they can't be tethered and hence use wireless communication, such as Wi-Fi, Bluetooth, or Med radio. The problem with wireless communication is that it uses 1,000 times more power than wireline communication for the same bandwidth. Therefore, wearable devices have a shorter battery life or need to be physically larger to accommodate a higher capacity battery. This can be particularly problematic for implanted medical devices since either that battery must be replaced more often or the devices need to be larger in size. Recently, human body communication was proposed as a solution to this conundrum. It provides the benefits of wireless communication, wherein the devices can be untethered and completely portable, while at the same time providing the power benefits of wireline communication. Human body communication works through capacitive coupling of signals from the transmitter into the human body, and the signals are similarly picked up at the receiver. The signals are entirely contained inside the body, which provides an additional layer of security. Hence, HBC can find application in any wearable device that makes direct contact with the body or is implanted inside. Some key areas are interpersonal information exchange, secure authentication, and for communication in wearable and implantable devices. Most prior scientific research has been limited to developing circuits and applications for human body communication. Few studies have been conducted to characterize the channel loss of the human body, but they either cover small frequency ranges that are overlapping or use ground-connected devices. Ground-connected devices means either the transmitter and receiver ground is connected to each other, or the transmitter and receiver grounds are connected to Earth's ground, such as in any benchtop measurement setup like a VNA or a spectrum analyzer. Ground-connected devices tend to underestimate the channel loss of the human body. This is particularly problematic since that model does not reflect the channel loss seen by wearable devices. Hence, there is a need to develop the channel loss model for the entire frequency range using multiple types of termination, such as the capacitive and resistive termination, and most importantly, by using truly wearable devices that do not have their grounds connected to each other or towards ground. This study should help form the backbone of the emerging field of human body communication by helping identify the optimum frequency operating point and by helping identify the maximum physical bandwidth. Before we move on to the measurement setup, let's have a look at the underlying mechanism or the biophysical model of human body communication as proposed by MIT. It is valid for low frequencies, which is the electroquasi-static region, and has a numerical limit of 10 MHz with a 5% approximation error. The transmitter is modeled as a voltage source with a series resistance, and the receiver is modeled as a parallel RC load. The forward path loss was found to be approximately 0 decibels, and the circuit is completed by return path capacitance. The return path capacitance is a parasitic capacitance formed between the communication device and the Earth's ground. The biophysical model can be simplified to the circuit as shown on the right, and the resulting simplified path loss equation becomes Cg by C body into Cg by CL. This is the reason why ground-connected devices incorrectly measure the channel loss since Cg gets shorted out. Additionally, Cg is directly proportional to the ground plane size of the measurement device, and hence it is imperative to have wearable devices which are of the same size as actual wearable devices while performing the channel loss measurement. As we move to frequencies above 10 MHz, the mechanism of human body communication transitions from electroquasi-static to electromagnetic. Cg still plays an important role in this transition, and hence a small device size is important. Also, at higher frequencies, a small device size will help reduce inter-device coupling. Measurements were performed in the anechoic chamber to prevent interference from outside sources and reduce multipath effect at higher frequencies. The measurements were performed in 3 cases. The first case was with a buffer attached to the receiver to simulate a high impedance load. The second case was with the receiver directly coupled to the body, which had an input impedance of 50 ohms to simulate the low impedance setup. And the third case, where the human body was removed from the picture to simulate inter-device coupling of the devices. The human subject was made to stand in the same posture, wherein the transmitter was attached to the left hand, which was raised at shoulder level, and the receiver was placed on the right hand, which was placed directly in front of the abdomen. 2 different transmitters were used for covering the entire frequency range. The first is a TIVA C-Series microcontroller, TM4C123GXL, which is used for the low frequency range from 100 kHz to 20 MHz by generating a PWM waveform. The microcontroller was placed in a 3D printed setup and connected to a battery to form the low frequency transmitter. The second device is a high frequency signal generator, which operates from 24 MHz to 960 MHz with a resolution of 1 kHz and a frequency stability of 0.5 ppm. The output signal power was 0 dBm at 50 ohms and had an accuracy of plus or minus 3 dB. The device body of the high frequency transmitter was made of aluminum that was internally connected to the battery ground. Hence, a layer of foam had to be placed in between the high frequency transmitter before being placed on the human body to prevent the ground plane from shorting to the signal plane on the human body. The receiver was a handheld RF spectrum analyzer from RF Explorer, which operates between 100 kHz to 960 MHz with a resolution of 0.5 dB, and the average noise level was minus 125 dB and had an accuracy of plus or minus 3 dB. The device body was again made of aluminum and was internally connected to the battery ground. Hence, it was placed in a silicone cover to prevent the ground plane from coming in contact with the body when it was being held. The device had an input impedance of 50 ohms. The buffer for high impedance measurements was made using a high-frequency buffer from Texas Instruments BUF602. It had a wide bandwidth of 1 GHz and a slew rate of 8,000 volts per microsecond. It internally generated the reference voltages, which is perfect for buffering high-speed AC signals. Using these devices, a standard procedure was developed and repeated since channel loss measurements are susceptible to variations. The subject was placed at the exact same location in the anechoic chamber. The transmitter was tied to the left hand, which was outstretched to the shoulder, and the receiver was placed in the right hand in front of the belly. The orientation of the electrode bands were kept consistent, and great care was taken to ensure a steady body posture while collecting the readings. Due to involuntary variations in posture and placement of devices resulting from human error, fluctuations in the readings were inevitable. This was addressed by repeating the measurements multiple times over the course of a few days and averaging the results. High-frequency and low-frequency channel loss measurements were repeated 10 and 3 times respectively. Each measurement involved collecting data for both 50 ohms and high-impedance measurements. 32 equally spaced points in logarithmic scale were taken from 100 kHz to 20 MHz. This was with the low-frequency transmitter, wherein a PWM signal of 3.3 volts was transmitted, which had 50% duty cycle. However, some frequency points, it was not possible to generate a 50% duty cycle square wave, and hence, a Fourier transform was computed for all of these PWM signals to calculate the V peak voltage at the fundamental frequency. High-frequency measurements were collected at 25 equally spaced points in the logarithmic scale from 24 to 960 MHz. The transmitted power was converted to peak voltage by the first equation given in the presentation. At the receiver, the received power was again converted to peak voltage using the second equation. And finally, channel loss was computed by taking the log of the peak voltages at the receiver and transmitter and were finally graphed. The channel loss measurements obtained have been graphed and can be seen on the figure on the left. Path loss at low frequencies is higher for low impedance termination, and there's a 40 dB difference at 1 MHz. The path loss for high impedance termination is ranging between 60 to 70 dB for this current setup, since it is a function of load capacitance and can move up or down if the design is tweaked. For the buffer that we have used and the current PCB design, these are the channel loss values we have obtained. As we start moving higher up in frequency, roughly beyond 10 to 20 megahertz, there are two physical signal paths available. One through the body, and the second where the devices radiate through air and couple. This happens because the wavelength starts becoming comparable to the coupling electrodes, and hence they start acting as poor antennas. The difference in path loss between high and low impedance starts reducing from low frequencies until it more or less equalizes at 60 megahertz. At this point of time, inter-device coupling also starts picking up due to electromagnetic coupling. At frequencies of roughly 100 megahertz and beyond, inter-device coupling starts dominating and is almost entirely responsible for the received signal at the receiver. The transmitted power peaks at 500 megahertz due to antenna effect of the devices, since the wavelength is exactly 4 times the device and electrode dimensions. In conclusion, channel loss measurements were presented across 4 decades of frequency to act as the backbone for human body communication. From what we have observed, high impedance termination offers much lower path loss at low frequencies, and inter-device coupling dominates the high-frequency measurements. Hence, it's very difficult to obtain accurate values of channel loss through the human body at high frequencies, and this motivates future research on optimizing the electrode coupler design and device design to maximize the signal transmitted into the body with minimal radiation leakage. Thank you.